So today we're going to talk about the antiderivative of inverse trig functions. But before we get into that, we are just going to do a quick recap on the derivative of inverse trig functions. So the first thing we need is the derivative of inverse sine, and that derivative would end up being 1 over the square root of 1 minus x squared dx. Okay. Now, if we were to have an x value that was not just x, but f of x, we need to account for that in our derivative statement. So again, we still have that square root of 1 minus x squared. Excuse me, this would now be f of x squared. And because we have an f of x, we have to apply our chain rule here. So the derivative of that f of x function would have to be included. So we cannot forget about that. The derivative of my inverse tan function is 1 over 1 plus x squared dx. So notice the difference between sine and tan. Sine has a square root function as well as a subtraction sign in between the two terms under the radical. And my tangent function does not have a square root, but it has a plus sign in between those two functions. Okay, so we need to be able to recognize those two differences. Now, just like we did with inverse sine, if I have inverse tan of f of x rather than just of x, I need to appropriately utilize that in my function, so I need my chain rule to be included there. All right, we cannot forget about the chain rule of that f of x function. Now let's actually get into our inverse trig functions, the antiderivatives of those. So the first one that we are going to discuss is the antiderivative of inverse sine. Now I'm going to write this in terms of a and u rather than in terms of x's and numerical values, because a lot of times with these inverse sine and inverse trig functions, it's almost like we're doing a u substitution here. So we need to make way for that. So if I have the square root and I have one function minus another function, oh, excuse me, that should be a minus sign there. Okay, so if I have one function minus another function and both of those functions are squared, that means that I'm dealing with inverse sine. So inverse sine, I would need my u value divided by my a value plus c. And again, I would need to incorporate any sort of u substitution that is going on. So the first function, the first example that we are going to do is probably the most basic one that you could have for our inverse sine. Okay, this could be rewritten as 1 over square root of 1 minus x squared dx. Now I'm going to figure out what my a squared value is and my u squared value, and from there I can figure out my a and u that I need in order to have my appropriate inverse sine function. So my a squared value is 1, therefore a is 1. My u squared value is x squared, therefore u is just x. And because I am technically using a u value here, I need to also know what my du would be equivalent to. Okay, so in this way, my du would just be dx. So let's rewrite things in terms of our a's and our u's, because that's the rule that we were given. So I have 1 over the square root of a squared minus u squared, and this dx value is the only thing that's left over, and that dx is equivalent to du. So once I have this setup is looking exactly like my rule up here, and I know that that rule is inverse sine, and it's inverse sine of my u value divided by my a value. and that u value. So now we're just going to go back and replace. My u value is x, my a value is 1, so I end up with the inverse sine of x plus c. Let's go to a second example. So I have the antiderivative of negative dx over the square root of 4 minus x squared. So first of all, I'm just going to kind of rewrite this a little bit. I'm going to bring this negatives in front of the dx out in front because that really is just a coefficient. And I'm left with 1 over the square root of 4 minus x squared dx. Now I need to pull out my a squared and my u squared. So a squared in this case is 4. That's the term without the variable. So therefore my a value would be 2. U squared is my x squared, so therefore the u value is x. Now I also need to realize that because I'm in terms of a's and u's instead of x's, when I take the antiderivative of this, I need a du rather than a dx. So just like with our u substitution, I need to take the derivative of that u statement. So let's rewrite this in terms of what's happening here. So I have the negative sign, and I have 1 over the square root of a squared minus u squared, and instead of this dx, I now write du. Well, again, as of before, this piece right here is my inverse sine function as seen and in the definition, and I have inverse sine of my u value divided by my a value plus c, and I cannot forget to bring that negative sign down in front. So I have the negative of inverse sine, and my u value is x divided by my a value of 2 plus c. Okay, that would be my answer. Now, our third example that we're going to do before we move on to our antiderivative inverse trig, again, just goes a little step further in our difficulty, but still the overall process stays the same. So my a squared, the term without the variable, is 5. Therefore, a is the square root of 5. My u squared would be 2x squared. Therefore, u would be x radical 2. And the derivative of that u statement would be radical 2 dx. So again, let's just kind of rewrite things here as 1 over the square root of 5 minus 2x squared dx. Now let's start replacing with our a's and our u's. So I have the 1 over the square root of a squared minus u squared. Now the only thing that I have left is dx. However, in my du statement, I have radical 2 dx. Well, I need just dx. So what am I going to do? Well, just like all of our other u substitution, I need to divide over that radical 2 to the other side. So when I go back over to my a's and u's, I have a radical 1 over radical 2 du that I have to add into our statement. So when I go through this, again, this is my inverse sine function of u over a plus c, and I have that 1 over radical 2 in front of it. So let's replace u and a with what it is equivalent to. So u is x radical 2, a is radical 5 plus c. Now, if this was a short answer, that could absolutely be your final answer. But if this is multiple choice, and questions like this more often historically are multiple choice, we would probably want to rationalize that denominator. So I have 1 over radical 2 inverse sine of x rad 2 over radical 5 plus c. So if we are going to rationalize that coefficient, I need to multiply the numerator and denominator by radical 2. And if I'm going to rationalize my f of x function, I need to multiply by radical 5, the numerator and denominator. So my final answer here that I think would show up more as a multiple choice would be radical 2 over 2 inverse sine of x radical 10 over 5 plus c. And that would be my answer for that antiderivative. Now let's move on to our antiderivative of inverse trig. So my rule here is that if I have the antiderivative of du over an a squared plus u squared, that's going to equal our inverse tan of u over a plus c. So very similar to our antiderivative of sine. However, for our tangent function, we also need a 1 over a coefficient out in front. So we're going to go through the same process that we did for inverse sine, okay, for inverse tan. So my first example, which is going to be, again, very basic, is dx, the antiderivative of dx over 1 plus x squared. Now, again, if I rewrite this as 1 over 1 plus x squared dx, my a squared is 1, therefore a is 1. My u squared is x squared, therefore my u is x. And I need du, which is equal to dx. So if we start replacing, I have 1 over a squared plus u squared, and I'm left with a dx, and my dx is equal to du. Well, what, don't you know, that looks exactly like the definition I see over here, except for the du being in the numerator. It's now off to the side as a separate entity. So this right here, we can go right to our inverse tan of u over a plus c with that 1 over a coefficient, and then we can replace what all those variables are equivalent to. So u is x, a is 1, and so then I have 1 over 1 as my coefficient out in front, which, as you can see, can just reduce to inverse tan of x plus c. So that ultimately is your most basic antiderivative for inverse tan. As always, though, things get more complicated. So our second example for inverse tan is going to start out with the antiderivative of dx over 1 plus 4x squared. So again, I'm just going to kind of rewrite this. So the dx is off to the side, and I have 1 plus 4x squared. Well, my a squared, that term without the variable, is 1. So a is 1. My u squared is 4x squared. Therefore, my u is 2x. And as always, because we're dealing with u instead of x, I need a du statement instead of a dx statement. So my derivative of u would be 2 dx. So let's plug in with what we've got. I have 1 over a squared plus u squared. Now the only thing I have left here is dx, but in my du statement I have 2 dx. Well, I need just dx, therefore again I need to divide both sides by that 2. So dx is going to be equivalent to 1/2 of du. So when I go and take my antiderivative, okay, this entire statement right here is my inverse tan of u over a plus c with that 1 over a coefficient. But I now need to bring down in front a 1/2 that I needed during my du statement. So let's see what happens. So I have my 1/2 times 1 over my a value, inverse tan of 2x, which was my u, divided by my a value of 1, plus c. Again, if it's a short answer, you could actually leave it like that. But if we're just going to simplify a little bit, that would become 1/2 as my coefficient, inverse tan of 2x plus c. And that is my answer. Let's do one final example of inverse tan before we end our video today. So the final one, and as always, I feel like they just get more interesting as we go. I'm going to rewrite this. Now, again, this 2 here is really just a coefficient. So I'm going to write that in front. I have 1 over 4 plus 9x squared, and I'm going to write the dx off to the side. So I don't want to get confused with anything. That's why I'm moving that coefficient out in front and the dx off to the side. So my a squared would be 4, which means a is 2. My u squared is 9x squared, which means my u value is 3x, and therefore my du would be 3 dx. So when I go to start replacing, I have that 2 there still. I have 1 over a squared plus u squared. And again, the only thing I'm left with is dx. So to get dx, I need 1/3 of du. So I have a 1/3 of du. So when I go to my next step, I have 2/3, and that's going to be inverse tan of u over a plus c, with that 1/a in front of my inverse tan. So let's go and replace. So we have our 2/3 times 1 my a value, inverse tan of u, which is 3x, divided by a, which is 2, plus c. Now I'm going to simplify this fraction in front, so 2/3 times 1/2 is just going to become 1/3 as my leading coefficient of inverse tan of 3x over 2 plus c. And that right there will be my final answer. So as you can see, going through all these problems, you have to be able to recognize the difference between inverse tan and inverse sine. But besides that, I have a very similar u substitution going on here. But instead of just u's and du's, we are now adding in those a's as well. Okay? So hopefully you guys found this helpful, and we will be doing more practice with this as well.